Hi everyone, this is Teacher Jane again. Our lesson for today is all about polynomial functions and their graphs. The examples that I'm going to discuss were lifted from the Mathematics 10 Quarter 2 module, pages 1 to 9. What is a polynomial function? A polynomial function is a function such as a quadratic, a cubic, a quartic, and so on, involving only non-negative integer and non-fractional powers of x. Do remember that it is not a polynomial function if a variable has a negative exponent or if the exponent is a fraction. So let us now apply this concept. Tell whether the following are polynomial functions. F of x is equal to x to the fourth minus x to the negative 2 plus 2x minus 9. Is it a polynomial function? No, since the second term bears a negative exponent. F of x is equal to 5x to the fifth plus x to the fourth minus 2 square root of x plus 5. Is it a polynomial function? No again, since the third term, negative 2 square root of x, when written in exponential form, will become negative 2x raised to 1/2. So, it becomes a fractional exponent. F of x is equal to 3x cubed plus 2x squared plus 1. Yes, it is a polynomial function. F of x is equal to 2x raised to the fourth power, quantity x minus 2 times quantity x plus 3. Yes, it's a polynomial function in factored form. Last, f of x is equal to 5x to the fourth minus 2x squared plus 3 over x. Is it a polynomial function? The answer is no, since the third term, 3 over x, when written in exponential form, will become 3x to the negative 1. So it means it bears a negative exponent. Since we know already what a polynomial function is, let us now determine the parts of a polynomial function. The standard form of a polynomial function is written as f of x is equal to a sub n x raised to n until a sub 0, or the constant of the polynomial function. There is one very important part of the polynomial function, which is the leading term. The leading term, you can find now the leading coefficient, which is represented by a, or the number before the variable x, and the degree represented by n. Let me first discuss how to determine the degree of a polynomial function. The degree of a polynomial function is determined by arranging the terms in descending order of powers, or what we call as the standard form. The term with the highest exponent, which is found in the leading term, is the degree of the polynomial. So let's have this first example. F of x is equal to x squared plus 4x cubed minus 2x plus 3. X squared is not yet the leading term. We have to arrange it first in the standard form. So the highest exponent is 4x cubed followed by plus x squared minus 2x plus 3. So therefore, 4x cubed is our leading term and it has the degree of 3. So our polynomial in this case is in the third degree. Let us now determine the degree of the following functions. F of x is equal to 4x squared minus 2x plus 2. First, is it arranged in the standard form? Yes. What is the degree? Second degree, since the leading term 4x squared has a degree of 2, therefore the polynomial function is in the second degree. Next one. F of x is equal to 2x cubed plus 4x to the fourth power plus x minus 2 is not yet arranged in the standard form. So let's arrange it first, which will come up to be 4x to the fourth plus 2x cubed plus x minus 2. Therefore, the leading term 4x to the fourth bears the degree of fourth degree. Next, f of x is equal to negative 2x squared plus 3x cubed. It's not yet arranged in the standard form. So arranging it in the standard form, we get f of x is equal to 3x cubed minus 2x squared plus x. Since the leading term is 3x cubed, therefore, this function is in the third degree. Moving on, let us now understand the effect of the degree to the zeros and turning points of the graph. So first, what are actually zeros and turning points? To begin with, let me discuss the zeros of a polynomial function. It only means that when a graph touches the x-axis, those points that touches the x-axis are actually the zeros of the function. Or in other words, they are called the x-intercepts, meaning these are the values that intersects the x-axis, or a point where y is equal to 0. Another name for zeros of a function is actually the root of a function, meaning it's the solution set where y or f of x can become 0. So, zeros is synonymous to x-intercept and root of a function. What about turning points? Turning points are actually points on the graph which leads to the maximum and the minimum points, where the graph fluctuates, meaning it changes its motion by either increasing or decreasing. So in this case, if this is your graph, the turning point will be at the maximum point. And if this graph continues, there's another turning point here, which is the minimum point. So let's now examine all the different types of polynomial functions in different degrees. So starting with a function at 0 degree, or what we call as a constant function. Now do notice that I'm going to determine here, did it intersect the x-axis? The answer is no. So therefore, it has no 0. It has no 0 or x-intercept. So I'm going to write no 0. I'll just write z. Now next is, does it have a turning point? Meaning, did it change or fluctuate to rise and then fall? Now, if you notice, it runs only on a constant motion because it's just a flat line. So, again, it has no turning point or no TP. Okay, second one, first degree or a linear function. Notice that a linear function is represented by a slant graph or a diagonal graph here. Okay, now let's examine. Did it touch the x-axis? Yes. It touched the x-axis at this point. And it touches the x-axis in one and only one point. So therefore, I'm going to write there, it has 1, 0 of the function or one solution set. Next, let us now check, did it change its direction or was there a turning point? Remember, it started with low, then it moved to going to the right, it keeps on rising and rising and rising. But it did not turn into a different motion of going down. Therefore, it has zero turning point. It has no turning point or zero. Okay, the degree. Second degree rather. Now let's check. First, let's check, did it intersect the x-axis? Yes, it actually intersects the axis into 2 points. So we have 2 zeros for the second degree. Now what about turning point? Remember, it started with a high point, then it went low here, but it turned high here. Okay, so there's actually a fluctuation. So we have 1 turning point for second degree. Now, I hope you can already observe that there is a certain pattern to the number of zeros and to the number of turning points as the degree of the polynomial increases. Now, let's go now to a cubic function or a function that is at the third degree. Now, did it intersect the x-axis? Yes. We have 1, 2 at the origin, and then you have the third point. So, we have 3 zeros of the function or 3 x-intercepts. Now, let's determine, does it have a turning point or does this graph contains more than 1 turning points? So, it started with a low point, then it rises or it increases. Then we have a turning point here. Then it went down. Then there's another turning point here. Then it increased again. So, as to turning points, it has 2 turning points. Now, I hope you can already notice that as the degree goes higher, the number of zeros and the number of turning points increases as well. What about the fourth degree? Okay, so it has 4 zeros. Okay, 1, 2. Now, this one is not an x-intercept, it's a y-intercept. Meaning it's a point where the graph touches the y-axis. So, 3 and then 4. Now, turning points, we have 1 here, 2, and 3. So, it has 3 turning points. Okay. Last is a fifth degree or a quintic function. So, obviously, it will have 5 zeros. Okay? And it will have 4 turning points. Now, we can actually now generalize a rule in determining the number of zeros and the turning points of a polynomial function and its effect to the degree. In general, the number of zeros of a function is given by the function has at most n real zeros, meaning whatever the degree of the polynomial function is already its maximum number of possible zeros. So, example, if it is in the fourth degree, it only means that it has at most 4 number of real zeros, but it could have 3, 2, 1, or no zeros at all. Now, what about the general rule for the number of turning points of a polynomial function? It has at most n minus 1 number of turning points, meaning if it is in the fourth degree, you have to subtract 1. So, there are only 3 possible turning points for that given polynomial function, and it could have 2, 1, or no turning point at all. To apply further what we have learned about the effect of the degree of the polynomial function to its number of zeros and turning points, let's check this table. Number 1, f of x is equal to negative x squared plus 2x plus 1 is in the second degree. That is why the maximum number of zeros that it would have will be 2, and the maximum turning points is minus 1, so you have 1. Second one, 4x to the fourth minus 2x squared plus 7 is in the fourth degree. So therefore, maximum number of zeros is 4 and turning points of 3. F of x is negative 4x cubed minus 6x squared plus 5x minus 1 is actually in the third degree. So maximum number of zeros is 3 and turning points is simply 2. Last, x raised to 7 minus 2 is in the 7th degree. Therefore, maximum number of zeros is 7 and maximum number of turning points will be 1. After discussing the degree of a polynomial function, let us move on now to the second most important part of the leading term, which is what we call as the leading coefficient. So, the polynomial function has a leading coefficient. Once the function is written in descending order of degree, or what we call as the standard form, the leading coefficient is the coefficient of the term with the highest degree. Let us remember example, f of x is equal to 3x cubed plus 2x squared plus 1 has a leading coefficient 3. So, because the leading term is 3x cubed and the number before x is 3, therefore, that is the leading coefficient. Since I have discussed the leading coefficient in my previous example, which is 3, now let us now go deeper by determining what will be the effect of the leading coefficient of the polynomial to the end behaviors of the graph. So first thing, let me define what is an end behavior. Okay. So example, if I have this graph, okay, it is actually two ends, the start and the end. So those are the end of the graphs, the start and the end. So this is the start and it ends here. Okay? So those 2 points are actually the ones that determines the end behaviors of the graph. So in this case, I started with a low point and it ended with a low point. So which means the end behaviors of the graph which I have drawn is a graph that starts with a low and ended with a low as well. Okay, so that is what we mean by the end behaviors. We are now going to determine how does the graph of a polynomial function behaves, okay, given a certain degree. I'm going to split my discussion to a polynomial that is in an even degree. So when I say even degree, these are polynomials in the second, fourth, sixth, eighth, and so on degree. For as long as their degree is even numbered, then they belong to this part. Okay, so let me show you this. Okay, so here it says here even degree polynomial. So my first graph is actually a parabola. Okay, a parabola, as we all know, is a quadratic function and its degree is in the second degree. Now, is it even? Yes, because it's in the second degree. Now, after determining its degree and it is even, these are actually the general rule. We start with what if the leading coefficient is positive. Okay, like in the example, it is positive 3. How will the ends of the graph behave? So, in this column, okay, these are actually positive leading coefficient, and this is in the second degree, okay. Notice that it started with a high point here, then it went low, but it ended with a high point again. So meaning, this is what we call as a high, high. Okay? It started with a high and ended with a high. So that's how it's going to behave if it is a positive leading coefficient and it is an even degreed polynomial. Now, let's examine now the next graph below. Okay, this is again an even degreed polynomial. 1, 2, 3. Therefore, this is a fourth degree polynomial. So, let's see. It started with a high point again, went low, went high, went low, but it ended with a high point again. So, therefore, to summarize, when the leading coefficient of an even degreed polynomial, okay, its end behavior would be high, okay, and then would end at also a high point. Okay, later on, I'm going to show you a summary or the general rule. Okay, let's go now to what if the leading coefficient of the even numbered polynomial is negative. Okay, notice that our parabola, our second degree polynomial, started with a low, high, then low. Okay, so the end behaviors are actually low and ends also with a low. Now, the next example below is a fourth degree with a negative leading coefficient. It started with a low and ended with a low also. Okay? Now, let me move on now to the odd degreed polynomial functions. So, when you say odd, it's in the first degree, third degree, fifth, seventh, ninth, 11th, and so on. Okay? So, I'm going to show you examples here. First one is a third degree. Okay, and the second one is a fifth degree. Okay, that's a fifth degree and a third degree polynomial function. Now, let's examine its end behaviors. Okay, this column, the leading coefficient is positive. Okay, so let's check. When it's positive, starts with low, then it ends with high. It starts with low, then it ends with high. So it is low and then ends with high. So it's a low, high end behaviors. Now let's move on now. What happens if the leading coefficient of the odd numbered polynomial function is a negative? It starts with a high, then ends with a low. So same here, which is hidden. It starts with a high and promise it ended with a low. So if it's a negative, it is high, then it is low. Okay, so that's the end behaviors of each polynomial functions. Okay, so which means the leading coefficient and the degree affects the end behaviors of the polynomial function. As to the degree, okay, even-numbered, even-degree polynomials would behave, no, take note, even-numbered polynomials will always start at the same level and will end at the same level. Meaning, if it started high, it will end up high. If it starts at low, it will end at low. While odd degree polynomials, Okay? Odd degree polynomials will have opposite endings. Or how opposite endings, meaning if it starts high, it's going to end low. If it starts at a low, it ends at high. Okay. So remember first these two concepts. Now, to help you remember this, let's see the general rule. The general rule for the end behaviors of polynomials can be summarized into this. So to help you out, if I were you, I'm going to clip this slide for you to remember the general rule of the end behaviors. So we start with the even degree. So even degree, these are the 2, 4, 6, 8 degreed polynomial functions. And the leading coefficient is positive. Okay? Your graph will start at high and would end at high. Okay. So moving on, if it's even degreed but it is negative, your graph will start at low and will end at low. A degree, these are the polynomials that are raised to 1, 3, 5, 7, 9, and so on. Okay? It starts at positive leading coefficient. If it's a positive leading coefficient, it's going to start with a low and ends with a high. Okay. If it's a negative leading coefficient, it's going to start with a high, then it's going to end with a low. I hope that you will remember all these things, the things that I've shown you about the polynomial functions. Now, in my next video, I'm going to discuss page 10 until the learning task that you're supposed to answer, okay, in our module in Mathematics 10, Quarter 2. The topics that I'm going to discuss in my second video are the following: how to find the zeros, how to determine the multiplicity, and how to graph polynomial functions. I hope you will watch my next video. Bye!